Hello and welcome to Empowered Learning. This video will be about how to calculate area and estimate area with finite sums. Or we can also say that this is how to calculate Riemann sums to estimate the area under the curve of a function. And so if you're looking at this video, then either you have started the concept of area under the curve in your calculus course, or you've already practiced the basic integration techniques doing antiderivatives and such, and now you're going back and you're studying this particular concept of area under the curve before you study the fundamental theorem of calculus, which actually bridges differential calculus, which is taking derivatives, and integral calculus, which calculates area under the curve of a function. So if you're looking at this video, that's kind of where you are. And what I'm going to do here to explain this concept is I have a prepared presentation here. I'm just going to read through it, and as I read through it, of course, I'll work out the examples where needed, and I'm hoping that you can follow along and sort of get what you need out of this. So at this point, we're making the transition from differential calculus, that is to say, finding a succinct way to express and find instantaneous rate of change, to integral calculus. And in integral calculus, we're concerned with the following questions. And I actually have three here. The first question is, when could I, quote unquote, undo a derivative of a function, and what information would that possess if I did that? Number two, how can I express the area under the curve or between two or more curves of a function and express that as some other function of x? And then the last question is, are the area under the curve of a function and the antiderivative of some function f of x related somehow? And so that last question I pose is because if you've watched my previous video that precedes this one, which is called Basics on Antiderivatives, then you would have seen how we actually took antiderivatives, that whole technique. And so now that we know that the area under the curve of some function is going to have something to do with the antiderivative, what is that relationship? And so in this particular section, or this concept here, we're actually going to address that at a theoretical level. So as we continue on here, we see that we have touched on the answer to the first question in the previous section on antiderivatives. So if you watched that video, then you know what I'm talking about. If you haven't and you still need to brush up on that, I encourage you to do so by watching that video. Now, in this section, we're going to address the answer to the second question. And by the end of our discussion on basic integral calculus, we will have addressed the third question. So right now, the purpose of this video is to dive deeply into answering that second question. And I'll go back to it again so that we all remember what it is. So it says, how can I express the area under the curve or between two or more curves of some function and express that as some other function of f of x? Okay. All right, so continuing on here, now turning back to the second aforementioned question, why would we even want to ask this question in the first place? Well, it turns out that the area under the curve of a function could have vital information that could be used to solve problems. Also, being able to express things such as some type of motion, rate of change, or phenomenon, etc., in terms of an algebraic function makes extracting information about these situations easier to do. So that's why we're doing this. Now, you have heard of the concept of area from geometry, and some examples of some of the shapes where there are known areas are the square, rectangle, a right triangle, or just a triangle in general, and a trapezoid. And if we put these particular shapes on an XY plane, this is an example of what it may look like. Okay, and so my point here is that if I wanted to look at a curve or some function that had the shape of either the square or the rectangle or the right triangle or the trapezoid in between some x values, and I wanted to figure out the area under the curve, well, that would be pretty easy to do. All I would have to do is just figure out what is the length and width of, let's say, the rectangles, or the base and the height of the triangle, or the base, the short base and the long base of the trapezoid in the height, and from that point, it's pretty easy. All I would basically have to do from there is just calculate the area. Okay, but if we look down at the next set of curves I have, which represents, we have the area a sub 5, which is the area under the curve of this first function, and a6 and a7, then we can see that using a square or a rectangle or a trapezoid, it's not going to be as easy. Okay, now, not impossible, but just not as easy. Okay, and so here these areas aren't as easy to calculate as areas 1 through area 4, which is the ones where we have the square, rectangle, trapezoid, wherever. Now, however, we could estimate the areas A5 through A7 by using areas of shapes that we already do know. Okay, and it turns out that the most common or most popular shape that is used to estimate the area under the curve is indeed a rectangle. And so what we want to do here is consider the area under the curve of this quadratic function here, just a parabola opening downward. And so it's f of x equals -1/4 times x minus 4 quantity squared plus 4. And we want to look at that in between when x is 1 and 5. So we want to look at it on that closed interval. If we attempt to estimate the area under the curve of the function f of x on this closed interval from 1 to 5 using 4 rectangles, the possibilities for how this could look are shown below. And of course, this is just 2 of the many possibilities, but this is the most common. And one thing I want to illuminate right now is that when I say if we attempt to estimate the area under the curve using 4 rectangles, another way that that is said is, instead of saying using 4 rectangles, it would say using 4 subintervals. And so my point here is that some textbooks like to say, let's do this by using so many subintervals. Other textbooks like to say, do this by using however many rectangles that we want. All I want you to understand is that it means the same thing, regardless. Okay. So what we want to do here is just attempt to find out the area under the curve. And what I've done here, I've drawn this using what we call a left endpoint estimate and a right endpoint estimate. And so let's look at the left endpoint estimate, or what I'm calling the underestimate in this case, to see why that is. Now, if you notice here, my actual function is kind of going like this, and it comes up and goes down, but I'm only looking at the portion of it from x equals 1 to x equals 5. And if you notice here, at each of these rectangles, I am taking the left top corner of it to be able to figure out what the height of the actual rectangle is. Okay, and so that's why I have these arrows here. And if I start from here and go this way, then that means I'm doing a left endpoint estimate, meaning I'm using the height of my function at, let's say in this case, x equals 1, to be able to figure out what is going to be the height of this first rectangle. And then I come here at x equals 2 and go up and figure out what the height of it is by using, when x is equal to 2, figure out what y is for the function. The same thing coming up here. And of course, I start for whatever that particular y value is, and then I move over from the left to the right, okay? And that's how I'm defining these rectangles here. I do the same thing for the right endpoint estimate, but instead of using the left upper corner to be able to define the height of the rectangle, I use the right, okay? And so what makes it different here is the values of x that I start and end with. And so that's the thing that's important. Whenever I do a left endpoint estimate, if you notice, I am using the x values for x equals 1, x equals 2, x equals 3, x equals 4. And if we look at that in terms of all the x values I have available to me, these are the ones that are the leftmost ones that I singled out. And if I look over here for the right endpoint estimate, then here I'm using the ones that are further skewed to the right. Okay? So, and I know that in all these cases, whether it's an underestimate like what I see here or an overestimate like what I see here, I know it's just giving me a rough estimate of what the actual area under the curve of our quadratic function, which is up here, in between x equals 1 and x equals 5, okay? Now, of course, we see here we have these gaps that are here, and so basically these are grossed underestimates here, whereas we see that a lot of the rectangle for here, here, and here is going to be above this particular function, so it's going to be a gross overestimate. But again, it's only that way because we've only chosen to use 4 rectangles to be able to figure out what the area is, or to estimate what the area is. Okay. Now, from what we can see here, since this is an underestimate here and this is an overestimate, we know that the actual area is going to be somewhere in between the left endpoint estimate and the right endpoint estimate. And one thing I do want to go ahead and point out now is that the only reason why the left endpoint estimate is the underestimate in this case is because this function starts out increasing and then it decreases. Okay, and for the right endpoint estimate, again, it starts off increasing and then it decreases. So functions that tend to do that within the interval of x values that we want to find the area for, the left endpoint estimate tends to be the underestimate. If we did just the opposite, if we had a parabola that was opening up, then our left endpoint estimate would be the overestimate and the right endpoint estimate would be the underestimate. Okay, so I don't want you to think that left endpoint estimates are always underestimates and right endpoint estimates are always overestimates. That's not always true. It really does depend upon the profile and concavity of the function itself. All right, so let's move on here. So now what we want to do is actually calculate what the area is going to be by finding the estimates. And we're going to find the estimates by essentially finding the area of each of the rectangles. Okay. Now I'm going to go back here for just a second to make sure that we realize one thing. And that is, for each estimate, whether it's the left endpoint or right endpoint estimate, do you realize that the width of each rectangle is only 1 full unit? Okay, and that is by design. And the reason I say it's by design is because here we know that the width of those rectangles, or what we're going to call delta x here, is just going to be the difference in between the highest x value and the lowest x value and the number of rectangles, or the number of subintervals that we wanted to have here. And so we see that when that happens, then the delta x, or the change in x values at each endpoint, is just going to be 1. Okay? So no matter how we try to look at it, when we look at this, the area under the curve there, it's always just going to be a width of 1. Okay? And so if we want to figure out the area of S sub 2, I'll come back up here for a second, Then of course we know the width is just going to be the difference in between 3 and 2, which is 1. But the height of the rectangle here is going to be 3. And of course that's because that is what f of 2 is. So if I took my function and I plugged in 2 into it, then of course this is what it would look like. And here I know that negative 2 minus 4 is a negative 2, and negative 2 squared is 4. And of course, negative 1/4 times 4, all that is just a negative 1. And then if you add 4 to that, you get 3. So that's how we got this number here, and that's how we know that the height of the rectangle S sub 2 is 3. Okay. So let's go back down here. So we know that this is going to be 3 times, and now this is going to be the difference in between 3 and 2. So this is the, we're going to call that the length, and we're going to call this the width of the rectangle. Or if you want, instead of looking at it as L and W, we could also look at it as height times width, if you want to look at it that way. Okay. But either way, it's fine. Here we're just going to look at it in terms of length and width. So I'll just go ahead and erase this. It's length and width. And of course, that answer is just going to be 3. Okay. All right. And so now if we look at S sub 3, if we look at our graph again, that's going to be the same as F of 3, which in this case is going to be about 3.75. And of course that width again of the rectangle is just going to be 1. But now that's going to be the difference in between 4 and 3. So we got 3.75. Okay. And so of course if we added all this up, and let me be a little bit more transparent here, this is about 1.75. If we added up all these numbers here, then we would get what the left endpoint estimate, or the left Riemann sum estimate of the area under the curve of our parabola would be. So we'll add those up at the end. Now if we do the right endpoint estimate, then pretty much everything's going to be the same, but now the height is going to be different. So now for S sub 1, we know that the height of that's going to be 3. Okay. And of course the width of that's going to be 1, or the length is going to be 3 and the width is going to be 1. Whereas for S sub 2, the length is going to be 3.75 and the width is still going to be 1. Okay. So we'll go ahead and fill in that information now. So we got 3 for the first one here. We got 3.75. And this is the difference in between 3 and 2, which is 3.75. For that next one, so we got 2, 3, so now at 4. And this would be the height of rectangle with S sub 3. Go up here to 4. So there would just be 4 times the difference in between 4 and 3. Doesn't look too hot, so let's get that looking a little better. Which again is 4. And then S sub 4, the last one here, this is what's a little different. So when we let x equals 5, of course corresponding y value is 3.75. Okay. So that is part of what makes that an over estimate. So it'll be 5 minus 4 there, and that's just be 3.75. All right, so now that we have the areas calculated for each of the rectangles in both graph A and graph B, our under and over estimate, of course if we add up all these numbers here for graph A, which is the under estimate, we'll get 12.5 square units. And if we add up all the numbers for graph B, we will get 14.5 square units. Okay? And we know here again that the actual area is going to be somewhere in between 12.5 and 14.5 square units. Now, what that is exactly, well, we would have to find another way to be able to get a more accurate estimate of that. And of course, one of the ways that we can do that is by increasing the number of subintervals, or put that another way, increasing the number of rectangles that we want to stuff in between when x is 1 and when x is 5. And the smaller the rectangles are, the more accurate of an estimate we may get. And so I have down here, just to make sure that we all follow what's going on here, I want to sort of formally talk about how we did these calculations by presenting some formulas here. And so if you notice, first thing I want to illuminate here is that when x is equal to 1 or 2, 3, 4, or 5, these are called our endpoint, or x value endpoints. The leftmost endpoints, like I've described before, are the ones that were skewed most to the left, which are these. And the rightmost ones are the ones that are skewed most to the right, which are these. And so in general, the areas S1 through S4 could be calculated by using this formula. And so this says calculate the area of the ith rectangle. And of course, x sub I just refers to which of these particular x values you're talking about. You plug that into the actual function itself, and we get the corresponding y value for that function, or if we want to look at it another way, we get the height, or the length, as we're calling it here, of a particular rectangle. And the delta x here is just, again, the difference in between the x values in which we have that closed interval divided by the number of rectangles, or if we want to interpret it as a number of subintervals we can do it that way. Okay. Of course, our a and our b come from the closed interval of x values. We've decided to take the area under the curve by, and we know that the area of a rectangle is just length times width, where f of xi again is the length of each rectangle, and delta x is the width. And so we could take these values here, the x equal to 1, 2, 3, 4, 5, and x sub I could be indexed to be able to label these. And so essentially what we've done here, I'm going to erase some of this so that I could sort of label before we go on to the next page, is that if I wanted to start off counting, let's say let I equal 0 and just keep on going, then here this 1 would be my x sub 0, 2 would be my x sub 1, 3 would be my x sub 2, 4 would be my x sub 3, and 5 would be my x sub 4. And of course, this formula here allows me to be able to come up with what these x values actually would be if I know what x value I'm starting at, and I know what my delta x should be. If I know that, then of course this I here just tells me, you know, I guess what x value I need to be at next. Okay. And again, the left endpoint estimate with I starts from 0 and goes on to n minus 1, and the right endpoint estimate starts when I is 1 and goes on to n. So that's another way you know that you're dealing with either the left endpoint estimate or right endpoint estimate. All right, so let's go ahead and look at how this looks when we use these formulas here. And so we see that for our estimate of the area a sub 5, we know, again, that since a and b were 1 and 5 respectively, then we have to do b minus a divided by the number of rectangles we wanted, or the number of subintervals, n, to be able to get our delta x, which again, if we're looking at our rectangles, this translates to the width of each rectangle that we're trying to find the area for before we add all those areas up. Okay. And just like I mentioned before, if we get our counter variable, which is I, starting at 0 and let that keep on going to 4, then we could use this formula to come up with the various x values that we need. So, of course, we're starting at 1, and when I is equal to 0, then, of course, we just have 1 there. When I is equal to 1, that means we need to skip over 1 width, or 1 delta x over, and of course that would be 2. Skip to the next, that'll be 3. Skip to the next, that'll be 4. Skip to the next, that'll be 5. Now, I'm not saying that you have to use these formulas to be able to figure out what your x value endpoints are, whether you're looking at the left endpoint estimate or the right endpoint estimate. But if you have like some funny numbers, it's a good way to know exactly which ones you're dealing with. Okay. Now, for the left endpoint estimate for the area A sub 5, notice that I can rewrite this as a sum of areas for each rectangle. And since delta x here is the same in each one, I know I can factor out the delta x out of each term. And essentially all I have here is f of x at that particular x value that we're talking about from this list. And of course, for the leftmost ones, we look at the sum of the corresponding y values for the function when we let x be 1, 2, 3, and 4. And then for the right endpoint estimate, it will be the same thing. We'll look at these x values and their corresponding y values and add them up and multiply that times delta x so that we can have the right endpoint estimate. And so here, if we want to express this in compact form, this is how it would look. So of course, sigma is the summation notation or summation operator within mathematics. And we just say, hey, starting from when I is equal to 0 and going to 3 as our counter, we want to sum up these areas. And this area is characterized by f of x sub I times delta x. And of course, if we write everything in terms of n, then we'll see that the n minus 1 is representing what 3 actually is. Okay? Because of course, in this case, we'll go from I equals 0, 1, 2, 3, and we would have reached the 4 subintervals or the 4 rectangles that we need. All right, so moving on here, if we did the right endpoint estimate, then we see that it's kind of the same thing, but of course we start at x sub 1, go to x sub 4, find their corresponding y values and add them up, and we could rewrite that as a summation of areas where the length of our rectangles is L and the width is W, where L is being represented by the height of our function here, and the width is being represented by delta x. All right, so now that we see that, of course, if we go and we actually calculate everything, you see that we still end up with the same numbers that we got last time. And so by seeing it this way, we know that as long as we can find out what the sum of those corresponding y values are for our function at each endpoint, whether we're doing left endpoint or right endpoint estimate, we can take that, multiply that sum by delta x, and bam, we have what we need. Okay. So again, the left endpoint estimate, 12.5 square units, is on the lower end, 14.5 square units on the higher end. So now that we see that we could estimate area under the curve of a function by using left endpoints or right endpoints, this is a good time to mention that we are not only restricted to only just using left or right endpoints to estimate area under the curve of a function f of x. If we randomly pick any x value within the interval, closed interval from a to b, and calculate other estimates as well. Okay. When we do this, we pick random x values within that closed interval from a to b, and we call these types of x values sample points, and we denote them by x of I with a asterisk, a star. Okay, and so what we're going to do here is actually do the same thing that we've done before, but we're going to do it using sample points. And what sample points just means that we're randomly going to pick an x value within the width of the delta x that we have. And so I'll illustrate that here. So of course we know that, and I'll write this again, our x of 0 is 1, x of 1 is 2, x of 2 is 3, x of 3 is 4, and x of 4 is 5. And if you notice here, the first x value for x of star is in between x of 0 and x of 1. The next one, x of 2 star, is in between x of 1 and x of 2. And x of 3 is in between x of 2 and x of 3. So x of 3 star is going to be strictly in between x of 2 and x of 3, so on and so forth. Okay, and so that's what I mean by although the delta x for all these is still just 1, we pick a random value of x that's in between them in order to get the height of our rectangles. So that's essentially what we're trying to do here. So if we want to figure out what the sample is going to be, of course, here the simple way to do it is, we know from what we've seen before, we can just say f of x of 1 star plus f of x of 2 star plus f of x of 3 star plus f of x of 4 star, and all of that can be multiplied by our delta x. And of course, we know that this is going to be f of 1.25, f of 2.5, f of 3.75, and f of 4.5. Add all that up and then multiply it times delta x. And so now, if we find out what these values are here, we'll find the following. So for f of 1.25, and I'm going to do this in decimal form just by using my calculator here, I see that this is going to be 2.109375. Okay. And if I do the same thing for 2.5, I see that I get 3.4375. And if I do the same thing with 3.75, then I'll get 3.984375. And lastly, with 4.5, I see that I'll just get 3.9375. And of course, all of that will just be multiplied by delta x, which we know in this example is just 1. Alright, and so now once we add all that up, we know that everything on the inside here is going to end up equaling 13.46875, of course, times 1, and that will just end up being just 13.46875. So we'll make a little room and write that. And that, of course, will be in square units. So in summary, we see that we have the area for A5, the left endpoint estimate is 12.5, the right endpoint estimate is 14.5, and we see that if we do the sample estimate, then that actually ends up being 13.46875. And I think I have a nice typo here that I need to correct right quick. So that should be a 5 and not necessarily a 1. And we see here that we know that the sample here is actually going to be in between what the actual value is, as well as and the right endpoint estimate, and we know that the left endpoint estimate is kind of way off there. Okay, so moving on here. So how do we find the precise value of the area a sub 5, or the area under the curve of that parabola that's opening down from x equals 1 to x equals 5? Okay, we have two ways that we can do that. And so one way is to increase the number of rectangles, or as we know, we can also say increase the number of subintervals that we want used to calculate that particular area. And of course, that just means increase the value of n. Number two, utilize a standard formula that will allow us to derive the area a sub 5 from our function f of x. And so choice 1 is where we are currently at, what we're trying to do. And choice 2 is where we will be by the time we end our discussion on basic integral calculus. And so if you're in a course to where you've actually looked at the techniques for taking definite integrals, and you've already talked about area under the curve there, then you've already seen what choice 2 is all about. And so you're just kind of going back in time now that you see what the result is, seeing how that actually came to be. If you haven't, or if you're not in a course that currently does that, kind of goes into the future and then goes back, then here that's kind of where we're headed. And so assuming that we have not seen that yet here, we are going to stick with our choice 1 for now. Okay, so let's go here. So we want to stick with our choice 1 for now. And if we're going to do that, let's increase the number of rectangles from n equals 4 to n equals 8. And this means that we will now stuff or try to fit 8 rectangles within the same space where we fit 4 previously. And if you see here, you see with the 8 rectangles, of course the rectangles are much more skinny, so the width is about half the size of what they were. And you also see that in this case, the left endpoint estimate, even though it is still an underestimate, it is not as bad as it was before. And of course, we can see that directly here just by looking at these places right here where we have these white gaps, and we see that the white gaps there are much smaller than what they were when we were just looking at it when we were trying to stuff 4 rectangles or fit 4 rectangles in between x equals 1 and x equals 5. Okay, so let's move on here, and we see that if we have these 8 rectangles, that of course our delta x now is about half of what it was before. Remember, it was 1, but now it's 1/2, because now we've changed n from being 4 to 8. And we also see that our endpoint x values change. And so instead of being 1, 2, 3, 4, and 5, now we have 1, 1.5, 2, 2.5, 3, 3.5, 4, and 4.5 for the left endpoint estimate. Now, if we were going to do a right endpoint estimate, then of course we would start here at x sub 1, and we would use all of these values and stop here at x sub 8. So now what we want to do is we want to use what we know from here to be able to calculate what our left hand endpoint estimate will be whenever we have 8 rectangles. Okay, and so this time I'm going to write this in summation notation form. So we have it like this, and this will go from I equals 0 to n minus 1 of f of x sub I delta x. And of course, I'm just doing a parenthesis there to say that all that is on the inside. Of course, that's I equals 0, and since n is 8, this would be 7 now. And this, of course, will still be f of x sub I times delta x. And if we write this out simplistically, we know this is just going to be f of x sub 0 plus f of x sub 1 plus f of x sub 2, and we just keep on going until we get to f of x sub 7. Take all that and multiply it times delta x. So in looking at it in that way, we know that, and let me move this down slightly here so that so we can see all the numbers there. So if we look here, this is f of 1 plus f of 1.5 plus f of 2 plus f of 2.5 plus f of 3 plus f of 3.5 plus f of 4 plus f of 4.5. Of course, all that is multiplied times delta x, which is just 1/2. And so now, of course, we can plug in these values for x into our function, figure out the corresponding y values, add them up, and just multiply them times 1/2 to get our answer. All right, so let's go ahead and write down this. So we know that when x is 1, we know that y is going to be 1.75. When it is 1.5, then it's going to be 2.4375. And let me try to write that again to make it look a little better. And f of 2 will just be 3. And f of 2.5 will be 3.4375. And f of 3 will be 3.75 again. F of 3.5 will be 3.9375. F of 4 will just be 4. And f of 4.5 will be 3.9375 again. And of course, we can multiply that times 1/2, which I'll just write in decimal form, which is 0.5. All right, so now if we take all those numbers and add them up inside the brackets there, that'll turn out to be 26.25 times 0.5. Of course, half of that is just going to be 13.125, or 13 and 1/8 if you want to put it in mixed number form. And of course, this would be square units. And as we see, of course, this number here is a little bit more accurate, but now it's closer to more on the left endpoint estimate, more so than the right endpoint estimate. And what I mean by the left endpoint estimate, whenever we were just dealing with 4 rectangles. And of course, that's to be expected since this is a left endpoint estimate as well. All right, so scrolling down here, we see that our result sort of falls in line. And of course, the actual area for a sub 5 will still be a value that's in between the left endpoint estimate when we have 8 rectangles and the sample one whenever we have just 4 rectangles. Okay. So now, what if we try to measure that area a sub 5 with 1 million rectangles? Okay. We would definitely get a result for A5 that would be really, really close to the actual value of A5. Of course, in an ideal world, we would like to stuff an infinite number of rectangles in between x equals 1 and x equals 5 to find the exact area for a sub 5. And it turns out that we can do precisely that if we evaluate the limit, and I'll underline that, the limit of our sum of rectangle angulars formula as n approaches infinity. So that concept of a limit that you thought you probably got away from after you studied limits at the beginning of Cal 1, it is back. And so if you are studying calculus throughout the different sequences, Cal 2, Cal 3, vector calculus, you will see that limit operator come up again and again and again and again. It is a basic concept in calculus to be able to study behavior. So we never really get away from it in this particular body of knowledge. So if we want to write what the actual area is in terms of what we call a right endpoint estimate, of course, we just do the limit as n approaches infinity of the sum. And of course, here you see how I goes from 1 to n. So we're indexing which rectangles we're talking about that way. For the left endpoint estimate, of course, the only thing that's different is our index starts at I equals 0 and stops at n minus 1 instead of starting at 1 and going to n. And then, of course, for a sample endpoint, we're just picking some, random value of x in between what our delta x divisions would be. So, of course, here we'll just be indexing that from I equals 1 to n as well. All right, so now let's apply our new knowledge to solving a problem where we want to find the distance of an object has traveled, but we only know information about the velocity of that object. So again, we want to apply our new knowledge, which is trying to find area under the curve of a particular function by solving a problem where we want to find distance of an object, but we only have information about the velocity of the object, okay? And before we get into this problem, let's look at the relationship in between position, velocity, and acceleration. And of course, if you're at this point in taking calculus, you've already talked about some of the applications of derivatives, so you may be familiar with this already, but I wanted to make sure I go through it just to be sure. So we know that position is the same thing as velocity times time, and the acceleration is the same thing as jerk times time. And this is not to be confused with that person that you don't like, okay? So we want to note that if position is non-negative, then position equals distance. And that means distance is speed or rate times time, where speed is understood to be the absolute value of velocity. So velocity is speed in a direction. So that means when we say a velocity of negative 2 meters per second, then we could be talking about a object falling down or moving to the left, or whatever negative actually means. Okay. Of course, when we talk about speed, speed is kind of like distance. Doesn't matter which direction you go, it's a non-negative quantity. So if we're going 2 meters per second, it doesn't matter whether we're going left, right, up, down. It's all the same. Okay. Whereas if we talk about position, of course, position is with respect to a fixed point. So we can have negative position and positive position. Okay. So we need to make sure that we understand that before we move on. All right, so we want to let S of t equal the distance or position, V of t equal velocity, A of t equals acceleration, and t equal time. And we also allow J of t to equal jerk. Now, in using derivatives, we can express the following relationships as follows. The derivative of position is going to be velocity. Derivative of velocity will be acceleration, and the derivative of acceleration will be jerk. And so if we express the relationships in between position, velocity, acceleration, and jerk as area under the curve of one of those functions, then it would look this way. So the area under the curve of some velocity function over some time, starting with an initial time t sub I and a final time t sub f, which we're calling here in these notes the closed interval from A to B. This would be represented as s of t, which would be the distance traveled during the time interval from A to B, basically. Okay, so the area under the curve of the velocity function is representing the actual distance traveled during the time. Okay, during the time from t equals A to t equals B. So similarly, we know that the area under the curve of acceleration will express the velocity from time t equals A, t equals B. And of course, for the jerk, which is rate of change of acceleration, we know that the area under the curve of that particular function will represent what the actual acceleration is. So now what we want to do is actually exercise some of these concepts that we've just learned in a distance problem example. So I'm just going to go ahead and scroll up here and let's kind of take a look at it. So we have a problem to where we have a speedometer reading for a motorcycle, okay? And we have a set of readings that are given to us in this table. And so we're saying that t is in seconds, and our velocity here is going to be in feet per second. So that means our distance is actually going to be in feet when and if we calculate that. So the first thing that we want to identify is what is the total interval of time speedometer readings that are taken, okay? And of course, we know that our time here is just going to be from 0 to 60 seconds, or basically 1 minute, okay? And assuming that the first reading, the 30 feet per second at time t equals 0, is the initial velocity of the motorcycle. So that means it's already moving, but we start timing it at a particular instance where it's traveling 30 feet per second. We want to sketch a graph of the table above and use the left endpoints of the interval to draw rectangles in the area under the graph to estimate that particular area. And we're going to assume here that velocity is constant in between the readings when estimating the area under the curve. Okay, so I'm going to set up a nice XY plane, probably for just quadrants 1 and 4, and show you how we can produce this graph. All right, so we have a nice XY plane set up here. And of course, in place of what would be our y-axis is now our v-axis, and in place of what our x-axis would be is our t-axis. And so we are going to use the initial velocity here to be 30 feet per second. Then of course we're talking about right here. And of course we're assuming that the velocity is constant in between readings. So everywhere from here to 12 would be about the same. So we would just draw it like that. And then afterwards, at 12 seconds now, that would go to 28. So that'll be slightly below. So we'll say about right here. And we'll take that across on to when that is equal to 24. So here I'm just going to make these little dashes here. And of course, kind of do the same thing here. And then at 24, of course, from there we'll go down to 25, which will be about right in here, like that. And then at 36, we'll drop down to 22, which would be somewhere in here. Drop down. And at 48, we're going back up to 24, So they'll be right under 25, which would be about here. And at 60, we would go on to 27. And 27 would come up here. It's at that point we would just stop. So let's go ahead and finish this up by doing a little dots here. This kind of, let's just get rid of that. So now that we got that together, what I want to do now is actually draw what this curve would look like. But before we do that, we have to understand that we were asked to do here in part B left endpoint estimates. So what that means is, if you notice, I came and I actually took the values to the upper left-hand corner of the rectangles to come up with what those particular heights of the rectangle would be. And so what I'm going to do now is illuminate those points in a different color so that you can see where those points hit at, and then from there kind of draw a continuous graph of what this looks like. Okay. But before I do that, again, I want to make sure that I stress that we came from here to there, and then 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 from here to there. And then of course we had to stop at that point. All right, so looking at this, you can kind of see how our function is going to look. I would have to start here, and of course at each one of these rectangles, the upper left hand corner is what is illuminated here, and that is how the function would go. So if I was to draw this, I'm just going to attempt to do this without hitting anything. So of course this function will kind of go like this, go down, come up, do like this, and then do like that. And so you see for the first two rectangles here, I would have, well actually first three, I would have an overestimate, whereas for the last two I would have an underestimate. And so the total area under the curve here, and I'll go ahead and illuminate that right quick. So here we'll just talk about all this area here. All the area of the curve there. Of course, we're going to get some of this stuff above as well, so we can see that. And that's what area we would actually be calculating there. Okay. So this is what the graphs look like. So we sketch a graph using the left endpoints. Here, if we were to move forward here and do the same thing, but now use the right endpoints, the only thing that would be different now is when we draw this, we would be using, let's say we would have started off at t equals 12 and then kept on going and went to t equals 60, and we would be doing right endpoint estimates, which would mean we would form our height of our rectangle by plugging in these values, and we would go from right to left to draw the top of the rectangles. So I'm going to pause the video right now and create another graph like this just to save some time, so that you'll see how it looks on the other side. All right, so I've drawn what the right endpoint estimate would look like if we were doing the same thing as we did in example B here. Of course, the only thing that's different now is, of course, this area under the curve here. Of course, we would shade all that, and we would see it would look similar. And I've taken the just like how I took the left hand endpoint values of the function, and I've taken the right endpoint values of the function here and sort of drawn a curve of what it would look like. All right, so let's go ahead and shade all this in now. Oops. Let's get that looking right. So we shade all of this, and of course we got all this here, all this up here, goes up through here, goes up through there, and all that stuff under there. And that's, in general, what the area under the curve of our velocity function would look like. So for part C here, we'll just say, look here for that. All right, so let's move on and finish up this example by going through the rest of the parts. So for part D, it says, estimate the area under the curve for your graphs in parts B and C. And so that is to say, first use the left endpoint estimate to estimate the area under the curve, and then repeat this process for the right endpoint estimate. And of course, we'll do that by basically adding up the sums of all the areas. So we're just going to say the area of the left hand sum or left endpoint estimate is just going to be, and we'll just go ahead and write it out here. So it's just going to be this first rectangle here. And of course, our delta x for all this will be 12. And of course, our heights here, since we're doing a left endpoint estimate, are going to be 30, 28, 25, 22, and 24 for the heights of our rectangles there. Okay, so this is 30, 28, 25, 22, and 24. Okay. Now, for the right endpoint estimate, we would start at 28, because that's what we see here, and do 28, 25, 22, 24, and 27. And then all that will be multiplied times our delta x, which would be 12 here, because all the rectangles have the same width. So that's what we are going to do now. All right, so taking what we had in our table, we know that the 30 that we have here, and I'm just going to use left hand sum estimate, this is going to be like the f of 0. This next one here is like f of 1. Next one here is like f of 2. This one is like f of 3. This one is f of 4. Well, I guess let me actually put the values in there, because I know that's a little bit confusing, because we did this in terms of units of 12 here. So let me do that correctly. So this would be 0, and then this would be 12, that would be 24, that would be 36, and that would be 48. That's how that would look. Whereas down here, this would start off being f of 12, f of 24, f of 36, f of 48, and f of 60. Okay. So now we just need to add up all these sums and then multiply them times 12 and see what we get. So if we add up everything and multiply the left-hand sum estimate or left endpoint estimate by 12, we get 1,548 feet. And if we do the same thing with the right-hand sum or the right endpoint estimate, we get 1,512 feet. So we know that the motorcycle traveled somewhere in between 1,512 and 1,548 feet within this minute here. All right, so we want to know for part E, so how do we interpret our calculations made in part D? In other words, what does the area under the curve for graphs in part B and C represent? Now, of course, we know that we just got through saying it, that the area under the curve here represents the actual distance the motorcycle traveled. Motorcycle traveled from when t was equal to 0 to t is equal to 60 seconds. And of course, our area for the left-hand sum estimate is the distance, and that is going to be 1,548 feet. And of course, the area on the curve for the right-hand estimate is also going to be distance, and that's going to be 1,512 feet. Okay, and so of course we just know it's just the distance that was traveled. And for F, we want to determine which estimated area L5 and R5, and so I'm actually saying it like this because that would be left-hand sum estimate using 5 rectangles, and this is the right-hand sum estimate using 5 rectangles. That's another notation for it. I'll come back up here to make my point. If you notice here, we had 1, 2, 3, 4, 5 rectangles, and 1, 2, 3, 4, 5 rectangles there. So that's why the notation is that way. And whenever you see L sub 5, that means left-hand sum estimate using 5 subintervals of 5 rectangles. Let's say if we had R sub 4, then that would mean right-hand sum estimate using 4 subintervals of 4 rectangles. So let's make sure that that's clear. All right, so here we know that so now that we're back, we see that the left endpoint estimate is the over estimate. So this is the over estimate. Let's just write that over. That's the over estimate, and of course the Riemann sum, or the right hand estimate here, is going to be the under estimate for this. And we know that, of course, if the actual area is going to be A, then of course right hand sum is going to be the under estimate, and left hand sum is going to be the over estimate. So it's going to be somewhere in between, of course, 1512 and 1548 feet. So now let's move on to part G of this example. So how could we express the distance of this motorcycle, the distance of motorcycle traveled, if you could record an infinite number of speedometer readings from the 0 to 60 seconds? That is to say, how do you express using an infinite amount of rectangles to measure the area under the curve between graphs B and C? And of course, what we're basically saying is we want to utilize that limit notation. And so what we want to do is do that using both the left endpoint estimate and the right endpoint estimate. Okay. So one way that we could do this is we could just say this is L to infinity, where we want to have the limit as n approaches infinity of the summation of I goes to 0 to n minus 1 of f of x of I delta x, or I guess in this case, since we have things in terms of velocity and time, we'll stick with the way that we're naming everything. So that'll be v sub t I. So we'll do it like this. Yeah, and then delta t. So that would be how the left endpoint estimate would be. Right endpoint estimate be limit as n approaches infinity again of the summation of I equals 1 to n of v of t sub I times delta t. And so that's how we would express the left-hand sum and right-hand sum if we had an infinite amount of rectangles we could put into there. And so what we're going to see later on, if you haven't watched those other videos yet, is that this will actually turn into the following. So we would say this goes from 1 to 5 of v of t dt. So both of these, if we could stuff an infinite amount of rectangles in it, it would turn into what we call here a definite integral. And again, if you haven't studied that yet, then of course you can watch my videos on the definite integral and see how all that relates. All right, so to close this out, so of course we now have the notation for being able to calculate the exact area under the curve using limit notation. But how are we actually going to do that? Okay, and what we do is we borrow from algebra sequences and summation sequences and series to be able to help us out. And so if we recall from algebra that a sequence is a function whose domain is a set of natural numbers, that is positive integers. And so I have an example of one such sequence here. And so for example, if a sequence is as listed, then its domain is just the numbers n, which is 1, 2, 3, 4, so on and so forth. And of course you can see here I have the alternating sign thing going on, and that's represented by the -1 raised to the n plus 1. And so that's what makes it change sign every time for every value of n that's even. Okay, but my point here is if you have identified a sequence, then there are certain characteristics that sequences possess. The sum of a sequence is called a series. So that's why it said sequences and series. And it's the series part that we're worried about or that we are concerned about, because we're trying to take a summation of basically areas of rectangles here by basically saying, well, let's assume that we're going to be able to stuff an infinite amount of those rectangles in between two x values to estimate the area under the curve of a function. Okay, so that's why the series part is important. So starting back here, we want to say that series also have special properties that help us to simplify some of the common finite sums in the first n numbers of a sequence. And so that is to say the summation properties of a series. And we can use some of those properties listed below to help us find the area under the curve of a graph. And after stating these properties, we will use this list to solve such a problem. So here we have, of course, the basic summation rule, which is if we have the summation of two particular sequences, then we can take the summation of each one separately and then just add those together. And same thing for the difference. The constant multiple rule basically says if we have some sequence that's a multiple of another one and c is any non-zero number, then we can just factor that out, figure out what the sequence is, well, the series is, or the sum of the sequence, and then multiply that answer times the constant. And then, of course, this last one here, which is the summation of any constant, is just another way of writing multiplication, which is how many times are we going to take that particular number n and multiply it or add it to c. Okay, and of course that's basically multiplication. Now what we are concerned with are these. And so we also know that the sum of the first n integers, which could be expressed here, and this is a k just in case you can't read it, and that's an n there, and that's k equals 1. So the summation of k, as k goes from 1 to n, can be rewritten as n times n plus 1, all that divided by 2. Okay. Now, for the first n squares, where we're talking 1 squared plus 2 squared plus 3 squared plus 4 squared, it turns out that the sum of the first n of those actually can be summarized as n times n plus 1 times 2n plus 1, all that divided by 6. And then the first n cubes, meaning 1 cube plus 2 cube plus 3 cube plus 4 cube, so on and so forth, is the same thing as we see here for just a summation of the first n integers, but all that's squared. Okay? And so these are the things that we will use whenever we do our summations to be able to help us out in finding out what the exact area under the curve is. And so I'm going to move on to the final problem that we're going to do in this particular video, and you'll see how we actually use that. And I've already written out the answers to this so that this can kind of flow smoother and you can actually see what's going on. So what we want to do is we want to use the graph of f of x is equal to x squared and other info given below to show the exact area A under the curve of some function is actually 1/3. And of course, we're looking at that area from 0 to 1. Okay? And we want to use the right endpoint estimate to calculate this area. So in looking at this, I'm going to scroll down a bit. I have a lot of prep work here so that we can kind of understand what's going on. We basically want the area under the curve from here to here of the function x squared. And of course, we're going to stuff an infinite number of rectangles there in between x equals 0 and x equals 1. And so any one of those rectangles is going to look like this, okay? Where depending upon what value of x I have, of course this goes from 0 to 1. If we put that in terms of n, that goes from 0 divided by n to n divided by n. And of course, any length here, or any width of our rectangle here would just be 1 divided by n, okay? And so, of course, that comes from what I'm talking about over here, okay? So we know that f of I divided by n, where this is going to be your x value there. And here we know that 1 divided by n would just be, any one particular length here. And of course, if we did this n number of times, we would get n divided by n, which would just be 1. So that's how we know that this ends up just being 1 divided by n for any given rectangle, okay? So, of course, we know the area is just length times width. We know here that the length is going to be the height of the function, okay, at some I divided by n. Of course, this is our generic way of expressing what x value we're going to pick, okay? And so we're doing that because we know that here, anywhere in between x equals 0 and x equals n, of course, we'll start here and we'll eventually end at n. Somewhere in between here is going to be some value of I divided by n, okay? And so that's why we have f of I divided by n, while I divided by n just talks about a particular random x value that's in between 0 and 1. And so if we do that, then of course we know that our width is going to be 1 divided by n, and we've already discussed that. And the height here, depending upon what I is, of course that'll be some number. And if we take that, knowing that our f of x is equal to x squared, then when we take this and look at the area, which is going to be length times width, or f of I divided by n times 1 over n, as we see here, our f of I divided by n just looks like I divided by n quantity squared, which looks like this. And of course, now that's important to us because now we have what our function is in terms of n, okay? And we also have it in terms of I. And of course, I, remember, is our index that we're keeping track of which rectangles we're trying to calculate the area of at a particular time. So the point here is to now have everything in terms of I and n. And so now we have that. So this a sub I here is actually just I squared divided by n squared times 1 over n. And that's essentially what we have here. And so now I just make my commentary here. Notice that I, in the information above, is keeping track of which rectangle in the infinitely many of them we are trying to stuff under f of x equals x squared within this closed interval. We are calculating an area for. Therefore, the first rectangle has a right endpoint of 1 over n. The second one has 2 over n, and the last one ends up being n over n. And so that's why I was saying that, based upon the I, depends upon which of those infinite number of rectangles we're talking about. Now, if we look here, if we do a right endpoint estimate, then that's going to start from I equals 1 to n of the summation. And so here, if we write exactly what I wrote up here, which is we take this and rewrite it, then we see we have I squared divided by n cubed on the inside of that. And of course, I can split this up this way. And the reason I want to split this up this way is because here, this particular factor is in terms of n. So that means when we use our limit operator down here, the limit is going to understand the 1 divided by n cubed. The limit operator will not understand the I squared. And so the I squared looks like a constant to it, okay? And so now when I take this summation that I have here, I'm factor out the 1 divided by n cubed because, again, the summation understands i's, and it's just stopping at n, but it doesn't know what n actually is. It understands I. So here for the summation operator, I is the variable, so it understands that, does not understand this. And so by having that, that actually makes our life easier because now we know that in terms of I, this is one of those summation properties that we studied earlier, okay? And I'm going to go back to that for just a second to make sure that you know which one it is. So we know that here, the summation of I squared, or the first sum of squares, and I'll go back to it now. If you see here, we have this particular formula, which is n times n plus 1 times 2n plus 1, all that divided by 6. Okay? So now that we see that, when we come down here, all of this just gets replaced with n times n plus 1 plus 2n plus 1 divided by 6. So that is all that right there. Okay? And so here I see we have an extra n cubed there, and I'm trying to figure out where that actually came from. All right, so I believe that's a typo there because I think that's not supposed to be there, so I'm going to go ahead and just get rid of that right quick. All right, so I fixed that, and so now you see here that all this, the summation of I squared as I goes from 1 to n, is just everything that we have on the inside there. And of course, if we take n and divide that by n cubed, we get a net n squared in the denominator. So now we have this expression right here. And so now when we say what is going to be the limit as n approaches infinity of r sub n, then of course we know that all this summation stuff that we did here it's just going to end up being just the n plus 1 times 2n plus 1 divided by 6n squared. And so from that point, we can factor out the 1/6, and this n squared we can break up as n times n, and we can put one of those n's with the n plus 1, another one with the 2n plus 1. So we can do it separate like that. And then from there, if we divide n plus 1 divided by n, we get 1 plus 1 over n. And same thing with 2n plus 1 divided by n, we get 2 plus 1 over n. And then we go back and we use the property that we know from the beginning of Cal 1. It basically says as x approaches positive or negative infinity for the function 1 over x, we know that the actual y values for the function approach 0. So that's what we have here. We show that, and then of course we got 1 plus 0 times 2 plus 0, which is 1 times 2, which is 2, and of course 2/6 is the same thing as 1/3. So that's how we show, using the properties of sequences and series, in particular of series, of how we actually calculate the area under the curve of a function exactly. And so where we're going with this is, of course, this is tough. This is tedious. Just like whenever you were studying the derivative of a function and you were having to do the limit of the difference quotient. Remember how that took such a long time to do. And so now we're asking ourselves, yes, this is fine, great. I know what the exact area under the curve is, but is there a better way? And so when we get into studying definite integrals and eventually the fundamental theorem of calculus, which you'll see in my other videos, that is how we actually find a better, more efficient way to be able to calculate the area under the curve of a function. So I encourage you to go and check out those videos, and hopefully you'll make the connection in between the two and see that doing the integration techniques that we go over in that video actually makes this process much faster than what we've done here. Okay. So I know this video is long, but of course there's a lot that's packed into that. So I wanted to make sure that we got it all and you saw some examples that kind of made the concepts that we're trying to convey here sort of glued together. So hope this helps. Take care.